in Alexandra University, and this piece of work was done in cooperation with my scientific supervisor, Professor Shurigin. So, I start with some basic notions from the theory of spaces over algebras. Weil algebra is an associative commutative algebra with a unital element, such that its only maximal ideal consists of nilpotent elements and factor A factored by its ideal is isomorphic to R. A height of an algebra is simply the degree of nilpotence, and a model is formed by n-tuples of an n-dimensional model over algebra is formed by n-tuples of elements of A. Okay, so let A be an algebra with the basis elements of A. So here we denote, we use the index with hat for basis elements that belong to the ideal, the maximal ideal. And let LA be an n-dimensional model with this basis. So just we have the basis in this module over as a real vector space, and here you can see the representation of an arbitrary element from LA. There are several models that can be associated with the arbitrary model over algebra, over Weil algebra A. So first, the model of tensor product. Its elements are of the form, and these elements form the basis in this tensor product, and there is a multiplication. The model of A linear A-valued forms on LA. So here you can see also the multiplication of algebra on this model, and the dual basis is defined as usual. The model of R-linear forms on LA, it is isomorphic to the model of A-linear forms on the tensor product. Just simply we substitute the coefficients. And we denote, sometimes we denote as far as there are two copies of algebra A in this tensor product. We usually denote the elements from the second copy with a prime. We denote by L0 the annihilator of A-linear forms in this tensor product. And this module L0 is spanned by vectors of this form. It is a basis in L0. And finally we can define a normalized A model. A normalized A model is a model LA with the choice of the module L1 such such that there holds such a decomposition of tensor product. So, and a module LA with a normalization chosen is called a normalized A module. So here you can see the basis elements in the normalization. We using the decomposition we mentioned above, the decomposition 5, we can decompose the dual space, the space of the module of R linear forms on LA, and here we denote A linear forms by LA star, L1 star, and the module L0 star is a submodule that annihilates L1, so our normalization. I recall the notion of a-smooth mapping. An a-smooth mapping is a mapping between two modules, AN and AK, such that the tangent mapping is simply a linear. And in coordinates it has the following form. As far we define an n-dimensional smooth manifold over algebra as a manifold whose with maximal atlas of charts which take values in the module AN, and the transition functions are a-smooth diffeomorphisms. As far as the tangent space to the manifold over Weil algebra carries the natural structure of a module, we can use the construction I mentioned above for the decomposition of tangent spaces in each point. So here you can see the basis. So dxa I is the standard tangent vectors. It's the basis in tangent space. So here you can see the basis in T0, and here you can see the normalization of n-dimensional A manifold. The normalization is a smooth distribution of such submodules T1 in each point, such that there holds this decomposition. So, and manifolds with chosen normalization are called normalized. It is the module, the basis of the normalization. And similarly, we can decompose the module of A-valued R linear one forms on MA. And the bases which correspond to this decomposition are mentioned in formula 13. So dx is the basis of L lambda 1 linear forms, and theta is the basis that corresponds to our normalization. And so we can take the submodule in the module of R plus S forms on MA, such that its basis elements are divided into two groups. So these forms are called pure or bigraded. So theta correspond to normalization again, and dx correspond to the alinear part. And taking the component of the exterior differential of the type R plus 1s, such that the increase of degree of the form is only by theta components. We get the differential, and that forms a differential complex. So the coordinate representation of this differentiation is in formula, you can see it in the formula 15. These complexes of this type were studied by Pierre Molyneux and Iso Weissman for folated manifolds, and there is an analog complexes for complex manifolds studied by Pierre Dolbeau. So, and now we can extend this notion of D-head complexes for the case of locally trivial fiber bundles. So here you can see the form of the differential pure bigraded form on the fiber bundle EA. So the only difference is that we have additional components corresponding to fiber coordinates, so dW. And the construction of the complex is very similar to that was mentioned above. And now let us consider the principal bundle, a smooth principal bundle over a manifold over algebra A with an a smooth structure group and GA. And we say that a connection in PA in the principal bundle PA is adapted if its connection form is alinear. So the connection form takes values in the algebra of GA. And we can construct the abstraction to the existence of a-smooth connections in PA So from this structure equation, we get that the differential d hat that we introduced of the form, the connection form, is the one component of the curvature form, and the curvature, and this component is closed. It's tensorial and it's closed, and so we can define a cohomology class that is called ITR class, and this class doesn't depend on the choice of the adapted connection in a principal bundle, and it turns to 0 when and only when the ITR class, there exists an asymmetric connection.
Any question?
Please give the most simple example of Weil algebra. The most simple, the least dimension.
Well, algebra of dual numbers.
Write down the relation.
So the basis is
Okay, so
Okay, if you take manifold over algebra and you change algebra to sub-algebra, what happens with manifold?
it is a submanifold.
It will be sub-manifold.
Yes, of course. So if we take a Weil algebras.
So maps between manifolds are defined in respect to algebra. Yes. So resolve algebra and tangent space.
Yes, actually. Yes.
Can you give an example of manifold, a smooth manifold with this connection and its curvature? Because
Well, I can give you an example of a smooth manifold, but with no connection. I haven't yet calculated the examples of curvature. So
do you have examples of different Delbour complex that really different from the standard Delbour? I mean that in your case you have your own Delbour complex, yes?
no,
Differential.
it is not. It is similar to a Delbour complex,
Yes, but
Yes,
but
analog
it is
of
not
Delbour.
really.
Analog of Delbour. But
Yes, yes.
I believe that
Just-
it is good to base such a generalization, such construction on some examples, some models. You need certainly need models.
Yes.
to the example that this complex is not the same as the standard Delbour complex, that it catches something more.
Other comments?
Yes. Can the structure of a manifold can be defined not through atlas but through some sheaf like we can do in smooth case?
Well, I guess yes, but I'm not sure I can write it.
Почему все-таки пучки тут тоже все-таки между схемой тоже через пучки можно определить только. Так что не совсем.
What is the purpose?
как раз максимально.
I think we can thank the speaker.